Hello, I'm Coleman Jonah, and I'm going to be giving a presentation on how to plot using Bode diagrams. Now, here is the example that we're going to be plotting, and you can see it asks us to plot the magnitude and phase of the following transfer function. And we will be using this chart to help us with the plotting. Now, the first step is to get the top half, the denominator, in the numerator to look the same as we see on the chart. So we want those to be in the same format. And the first step for the top half would be to factor out 1s. You can see here, factored out an s. The second step will be to factor out 2 from the inside of the parentheses on the top half. And that will get us 10 times s times 2 times s over 2 plus 1. And we see that s over 2 plus 1 is the same as in our chart over here. So we have 1 plus j omega. It's the same as s over 2 plus 1. Next step, we're just going to condense down the top half. So we have 20 times s over 2 plus 1 for the top half. And so now on to the bottom half. And the first step we're going to do is, like we did in the top half, factor out so that we end up with a plus 1. We always want to have a sum term plus 1 within the parentheses. So for the first case here, we had to factor out a 4. So we went from s plus 4 to s over 4 plus 1 times 4. So we just factored out a 4 there. And for the second one, we went from s over 2 plus 20 to s over 40 plus 1. So all we did there was just factor out a 20. And now we're going to condense those terms down to have 20s on top and 80 on bottom. You can ignore that s, that was a mistake. And now, after reducing that fraction, we end up with s times s over 2 plus 1 divided by 4 times s over 4 plus 1 times s over 40 plus 1. Now, the next step is to plot the magnitude. So this starts by on a semi-log graph paper. See, I put our chart over here for reference, our equation on top, and I've already drawn our axes on the page. So the first thing we need to do is, on the chart here, we can see that a constant k will result in a magnitude of 20 log base 10 of k. And because we have 1 over 4 as our k value, we do 20 times log 1 over 4, which equals negative 12.04. And now another thing that we need to be careful of is, because we have this s on top, we need to add 20 to our starting point here. So originally our starting point would have been just k, or 20 log base 10 times k. But because we have this s term here that's outside the parentheses, we need to add 20 to it to get our actual starting term. And this point puts us right here at 7.95. The next thing we do, you can see, is we move on to the next area of our chart, and that would be j omega to the power of n. And j omega to the power of n, in this case, is s, and n being 1, because it's s to the power of 1. It's just not shown there. So s to the power of 1 will result in 20 times n decibels per decade gain. And this is drawn here with the dashed line. So the next thing that we have is the s over 2 plus 1. And this can be seen in this part of the chart, so the second to last part of the chart. We have 1 plus j omega, which is the same as 1 plus s, over z, and our z is 2. So we have s over 2, which means that we have a gain of 20 decibels per decade starting at z, which is 2. And it starts right here, you can see. And this goes up until the end of time. So these, even though they're not drawn as going out of the page, these will go on forever. The next parts that we have are the negative parts. and that is on the bottom of the function. So we have s over 4 plus 1, which if you look at the bottom of our chart, is in the term of a reciprocal. So we have 1 plus j omega over p, which is 1 plus s over 4. So in this case, our p value is 4. So we have a gain of negative 20 decibels per decade starting at 4, which is right here. And continuing on, we have the same of s over 40 plus 1. For this one, our p-value is 40, so we have another gain of negative 20 decibels per decade starting at 40. So now the thing to do is to make our final graph by adding these together. And to start, we need to add our line that consists of the first part from our S value. So our S value by itself contributes 20 decibels per decade for all time. So we started way at the beginning of our graph, and now we're going up to the point here. And we stop at this point because it's where we have another gain start. So right at this point, we have another 20 decibels per decade gain start, and that is from the S over 2 plus 1 term. And that moves on to 4 decades, or sorry, that moves on to 4, the value of 4. And the reason we go up into a value of 4, so we plot, this is a gain of 40 decibels per decade up until the value of 4, is because we have another gain start at this value of 4, and that is a negative 20 decibels. So this will cause our line to go back to a gain of 20 decibels because we have 20 plus 20 is 40 here, and then minus 20 brings us back to our original 20. And this goes up until the 40 value of 40, because at that point we have our other gain start of negative 20. And at that point we have 20 plus 20 minus 20 minus 20. So it goes back to being flat, and that will go on for all of eternity. And this black line is our final magnitude plot. Next, plotting the phase, we will keep our equation as is. We don't need to change anything. And for phase, if you look on the right side of the chart, a value or a k value of 1 over 4 contributes nothing to the phase. So start at 0. But the s value contributes 90 degrees to our phase. So we will start at a value of 90 degrees. And as before, we'll move on to our numerator terms first. And in this case, we have s over 2 plus 1. And so our z value is 2. And our phase will start at a value of z over 10 and go on to a value of 10 times z and have a gain of 20 decibels or 20 degrees over that time period. So you can see we have our contribution of the 90 degrees from the S term, and then we have our contribution of the 90 degrees over 2 decades from the first S term. And from there, we have our negative S term, which will contribute negative 20 degrees, starting at its z value of 4, and moving on to the value of 40. And similarly, the other one, we have s over 40, so it starts at a value of 4, and it has negative 90 degrees until a value of 400. Now we'll start to add these together to get our final plot. So our first line here starts at 90 because of the S term, and it goes until the starting point of point 2. So from point 2, we'll start moving up at a value of 45 decibels per decade until we get to point 4. And from point 4, we have negative 45 decibels per decade, so it goes back to being flat. And we'll continue being flat until we reach the 4, value of 4. And starting at a value of 4, we'll go even more negative because now we're at negative 45 plus negative 45 plus 45 is negative 45. So our gain is negative 45 until we reach a value of 20. And at 20, we're no longer receiving the gain of 45 decibels from the s over 2 plus 1 term. So it will start to go even more negatives. Now we're going at negative 90 decibels per decade because we have negative 45 plus negative 45 until a value of 40. Starting at 40, our s over 4 plus 1 term has stopped contributing. So now we're back to negative 45 until our s over 40 plus 1 term stops contributing at a value of 40. From there, it will be flat or have no gain until infinity for all time. I hope this example has been helpful. Make sure during tests to label all of these points that I've circled throughout the presentation and to label the slope of all of your lines. So I hope this has been helpful, and thank you for listening.